All right. So the stream title is a series of remarkable coincidences or coincidences. One of those is the technical term. Okay. So what we have over here is I claim, is a mass energy bank of universe. Why? Because I believe it was Julian Barbour that said that on his tombstone, he does not want pepperoni and cheese. He wants nothing but ratios, because that's his whole big thing. Because these ratios between different stuff doing different things within our realm of persistence lead to basically reality as we know it here. Okay, how the heck do I get this number? It's 7.488 times 10 to the 78 joules. What the heck is even that? Okay, so we're following at least the concept of maximal extendability. And what is that? No arbitrary boundaries. Essentially, if you're going to assume that we can continue to go down smaller and smaller and smaller, and we can do that infinitely, well, then by extension, you're going to say, well, if we can go down infinitely, then things will just get bigger infinitely. Okay, I mean, that's a logical framework. Personally, I happen to believe that there might be a limit to space as we know it, or at least that we could calculate. Now, we might not necessarily be able to observe that on our meterish level or something like that, but perhaps we could in the future. Okay, so the whole claim is that we're taking that thingy over here. What is this thingy? We're taking our reference length, the meter, that we have for our coherent system of units. And again, a coherent system of units follows these three little thingies here. FEP, FEP. What the heck is that? F equals ma. You may have heard of that. That's force equals mass times acceleration. Okay. And then energy equals force times distance. It's that force used to move something a particular distance, and that's energy. Okay. Now, you also have power, which is energy divided by time. So basically, your computer, or at least my computer right now, it's using energy. Now, if I unplug my computer, one, it's probably not going to do as well. But number two, it's then going to have a limited amount of power that it can run for a duration of time. See, energy divided by time over here. And then it will power off because it will be out of power. Okay, so that's a coherent set of units. So the claim is that if we had some logical way, and again, could be completely wrong, if we had some logical way to calculate how much mass, energy type stuff could be in universe. Okay. So the claim is, if you happen to take this ratio of 1 meter, our reference of length, divided by the minimum of length, the Planck length, and we have that ratio, and then we square it because, well, we like doing that in physics. I think Professor Carroll had a video at one point in the Biggest Ideas of the Universe series where he's like, well, in physics, we like to look at the relationship between different things, and sometimes if that doesn't make sense, then we square the result and we can see if we can interpret it. So I'm like, that's cool, let me do that. And then the interesting thing is, when you do that, you get your giant number. You're like 3 times 10 to the 69. Ginormous number. Now, if we take that ginormous number, and then we multiply it by the base of mass, the Planck mass over here, okay? If we take that, we're going to get still a really big number, but that's the -8 power, so you basically knock off 8 of the exponents, so you get that 10 to the 61 kilograms. It's about 8 times the magnitude of the estimated total mass stuff in the universe. Okay. So that's going to be important. So basically about 100 million times more than what we can see in the observable universe. Okay. So if we take that, and since mass can be converted to energy via good old Albert Einstein, E equals mc squared, and that's a big number. That's already got like 16 orders of magnitude, or basically you throw an extra 16 zeros after something. Basically, you're going to go from like 10 to the 69 to that 10 to the 61 kilograms. Excuse me, I'm doing that wrong. We already said that part. If you're taking that 10 to the 61 kilograms and you turn that into energy, you're going to get this number here. That 7.488 times 10 to the 78 joules. I am saying the digits as well because this is important. Why? Because if we go a little bit over, you're going to see I wrote down this thing called the Planck spring constant. And if we notice, it happens to have the first beginning digit, 7.488, times 10 to the 78. Seems to be the same number. The dimensions are different. That's kilograms divided by seconds squared. Why? Okay, so now this is something probably a first-year physics student could actually explain better than I could, because again, I haven't ever finished a full official physics class. We're going to start to go through, I think, some of the MIT lectures and stuff, and then Thad's going to actually start like doing some, basically helping to teach me and do some elementary classical physics and stuff like that, just because that's useful stuff and it's fun. It's fun, actually, learning different things. And especially if you happen to have an online calculator like Wolfram Alpha that does a lot of the hard stuff for you, but at least getting the concepts down so we can try to figure out what the heck's going on. Okay, so the spring constant, it has something to do with if you've actually done physics, and basically if you have a spring, an idealized spring against a wall, it's on a block of mass. Okay, now we throw out friction and all that other jazz. We're assuming there's no friction or anything because we want an easy calculation. So basically, if you tweak that mass and it's going to start to oscillate, it's like, oh, it's kind of like a harmonic oscillator. So the spring constant, its dimensions, as we can see, it's kilograms divided by seconds squared. Okay. How the heck do I know this? It's because Wolfram Alpha told me, and a lot of times it's people like to go down wiki holes. I often go down Wolfram holes, in that you never know where you're going to. Basically, it's a computational database that Stephen Wolfram is an absolute mad lad, in my opinion. Finally, actually created the thing that he had conceptualized when he was like 10 or 12 years old. It's like, well, we have computers, we have a bunch of information. Well, what if we use computers that had that information that could compute that information? It sounds like, oh, there's no reason why you can't do this. That might be true. Now, actually pulling it off is a whole different ballgame, because if anybody's ever done programming, there's a lot that can go wrong. Okay. Poindexter is saying that I think we're in a closed system. I'm very sympathetic. I'm basically kind of claiming the same thing, that we're basically in an N hypersphere of maximal volume. And we can go through the reasons for that maybe at the end, if not, maybe another day. Okay. So, but what the heck is a spring constant? Okay. So the only reason I know this is because a lot of times you'll see different Planck units. Like you're going to see our friends, you'll see very often the Planck length, the Planck mass, the Planck time, the Planck temperature, and sometimes you'll even see the Planck charge pop up. Okay. So the claim is those are bases of reality, aka they're important things. Why? Well, because from those units you can create, at least to first level approximation, most of the constants of nature. So at least some of the most important ones that I don't think many people would argue about. So let's do this right here. Okay. So the claim is we have this thingy right here. Okay. So let's do this. Okay, so we have our reference of length, the meter, because we're using a coherent system, divided by a minimum of length, and we're squaring it. All right, it gets us that 3 times 10 to the 69 number there. Okay. Now, we toss in the Planck mass. It's got a magnitude of 10 to the minus 8, so the exponent's going to go down by about 8. So I get, 10 to the 61 kilograms. And then, by the magic of E equals mc squared, I just raise it to c squared, the speed of light squared. And then we get this number here. So that's where that number comes from. Okay. So now where the heck does the Planck spring constant come from? Now, a lot of this, I think I was just multiplying and dividing different things, just playing around, going down a Wolfram hole. And then you come across something like this. What's this? All it is the Planck mass divided by the Planck time squared. And I would see this number, and I have no idea what the heck this number is. Kilograms per second squared. I didn't need to know. because Wolfram alpha tells me, oh, it's a spring constant. Huh. Now you can go through more. You could say it's a spring constant, a force gradient, stiffness, surface tension, Peel strace, spectral radiant energy, density with respect to wave number or cleavage. Okay, so those are interpretations of this thing here. Something like spring constant. It just says spring constant. That's usually something you figure out when you have like a mass attached to it. This happens to be a mass energy that happens to have the same magnitude. Well, that's interesting. What gets more interesting is, again, what is the difference? So if you just look at the dimensions, because, this one. So for a spring constant, it's mass divided by time squared. Cool. What's this? This is energy. And again, mass times, well, this is essentially c squared. Why? Because a length divided by a time is a speed. And if we're talking about a minimum of length divided by a minimum of time, that should give us a maximum of speed. The speed of light. It's squared here. Okay. So if you can see already, there's going to be a very particular difference there. And that difference is going to be 1 meter squared. So our reference length squared. Huh. That's interesting.